Okay, we will start. Okay, so today the second part of server architecture, the remaining part. So we will talk about the edge computing architecture for the Internet of Things. It means edge computing architecture for the IoT. So edge computing is a paradigm that brings computation and data storage closer to the source of data, such as IoT device, rather than relying solely on centralized cloud-based system. This this approach minimize latency, reduce the bandwidth usage, and enhance data security, as well as improves the response time. So the key components of edge computing architectures are components of sorry components of edge computing architectures are IoT device and edge nodes, fog layers, cloud backends. So the second key component will be architectural model, like device to edge. IoT devices send data directly to the nearby edge nodes for processing, and the device to fog to cloud. It means data flows through an intermediately fog layer before reaching to the cloud. Then other one is hybrid models. Hybrid model is combine of local processing at the edge with periodic synchronizations with the cloud for advanced analytics. Uh, then third one is key characteristics like data central decentralization and low latency with scalability and energy efficiency. Decentralized means reduce the reliance on centralized data centers, and the low latency mean process data close to the sources, enabling real-time response. It mean uh, it will enabling the real-time response to the process of data. So the scalability support a growing number of devices and data streams. Energy efficiency means reduce the energy consumption by limiting unnecessary data transmission. The applications in IoT, industrial IoT things, IIoT, real-time monitoring of manufacturing equipments, smart cities, traffic management, surveillance, and waste management. The traffic management, I think now in Sri Lanka also this is integrated. Most of cases, the device IoT devices analyze the speed and other things of the traffic. Then it will share the details with the police database. Likewise things. Then the healthcare side, remote patient monitoring and medical diagnostic, retails industry, and agriculture. Of challenges and considerations in edge computing architectures are data security and privacy. Those are challenges, and interoperability, resources constraint, and scalability. Those are some major challenges which is shown in the edge computing architectures. So the emerging trends will be AI at the edge, like incorporating machine learning models for real-time analytics and decision making, and 5G integrations, leverage of 5G networks to enhance connectivity and reduce latency, and the serverless edge computing using lightweight event models for edge operations, zero trust security models. It means enhancing security frameworks for edge environments. So the edge computing architectures are pivotal for unlocking the full potential of IoT, enabling more efficient, secure, and scalable systems that cater to the growing demands of modern applications. Now we will go to the expansions of growth The exponential growth of IoT data explosions, and new opportunities. So the rapid proli sorry, proliferation of IoT device is driving an unpredictable explosion of data. This exponential growth is repression repression in the industry presenting both challenges and opportunities. So the exploration of dynamic behind IoT data growth and the opportunities it creates. So the scale of IoT data provision, data explosion. So the proliferation of devices by 2024, it means in this year, the number of IoT connected device is projected to surpass 75 billion geographical. It means in the this year they are planning the general plan for IoT connected device is surpass 75 billion globally. So the next thing is this can be IoT is the next next generation thing. So this is going to be happening this year mostly. It will be surpass everything mostly. So the data volume is IoT generate vast amount of data daily. For example, autonomous vehicle can produce up to 40 terabyte per hour. So the data velocity, data variety, those will be the scale of IoT data explosion. Then the drivers behind the data explosion will be smart devices. Rapid adoption of smart homes, wearable devices, and industrial sensors like the Apple Watch and the Fitbit watch. The smart watches will be wearable devices, and the smart glasses now available. So those will be the drivers behind the data explosion. The 5G networks, upgradable hardwares like the decrease in cost of sensors and IoT device, accelerate adoption across industries, the data intensive applications, emerging applications like autonomous systems, augmented reality, and digital twins. So the challenges associated with the IoT data growth is mostly data storage. The traditional centralized storage solution struggle to scale the sheer volume of IoT data. Then the bandwidth. The network are strained by the need to transmit high volume of data to centralized system, and the latency requirement is there. So the real-time applications like healthcare monitoring and autonomous vehicle demand low latency process, because for the healthcare monitoring it need to be done in real time. If any delay is there, the result, it may be mostly in the healthcare, the result is not real time. It will be affected to the life, human life. So the then other one is security and privacy. Managing sensitive IoT data raises concerns about breach and unauthorized access. The next we will talk about the new opportunities arising from IoT data, enhance analytic and AI, edge computing, digital twins, smart cities and infrastructure, healthcare innovations, supply chain optimizations. Those are the most new opportunities will be arising from IoT data. Then struggle strategies to manage and leverage IoT data. Scale storage solutions adopt distributed storage systems like cloud and hybrid models. Then the AI and machine learning automate data processing and extract actionable insights from massive data sets. Then the data prioritization, interoperability of standard like adapt stand to enable seamless integration across drivers IoT ecosystems. So the future outlook will be hyperautomations like integration of IoT with AI and machine learning to drive full automated systems. Then decentralized architectures, growth of edge and fog computer for localized scalable solutions. Then sustainability focus, leveraging IoT for efficiency, energy use of waste reductions and environmental monitoring. The exponential growth of IoT data is double-edged sword. While it's challenging traditional systems, it also creates immense opportunities for innovations. Like it will be challenging to the traditional systems. At the same time, it will be giving more opportunities for innovations and efficiency and the growth across industry. Strategic investments in data management and processing technologies will be critical to unlock the full potential of this data explosion. So the next one is IoT device limitations, processing and storage. IoT devices are integral to modern ecosystem, yet their capabilities are often limited by hardware and operational constraints. So the understanding these limitations is crucial to design robust IoT systems that optimize performances through effective strategic like data offloading. Key limitations of IoT device: processing power. And processing power, IoT device such as sensors and accurate often having limit CPU or microcontrollers, and that they struggle to perform complex computative or run resources intensive algorithms like machine learning locally. Then other limitation will be storage capacity. Many IoT devices rely on small embedded storage modules, often in range of kilobytes to a few gigabytes. So the high frequency data generation can be quickly exceeded storage capacity, necessitating offloading and external systems. Then the other key limitation is energy constraint. Battery power of IoT device must conserve energy, restricting continuous processing or data transmission. Energy intensive tasks like real-time analytic or frequent network communications are not sustainable. Then other limitation is network bandwidth. So the limit bandwidth can be caused to bottleneck, especially for devices transmitting large volume of data like video stream. So the network congestion may result in data loss or latency, impacting real-time applications. So other one is key challenge is security limitation. Limited computational resources hinder the implementation of advanced encryption and authentication mechanisms. Vulnerabilities may expose device to attacks such as data breach or unauthorized controls. So the other thing is resources constraint and their impacts. It like real-time processing. So the device may experience delays or fail to meet real-time requirements due to inadequate processing speed. Data retention is storage limitation prevent long-term data storage. So the function limitations of functionalities. So this will converse resources devices may compromise on features such as lower sampling rates or less frequent updates. So the roles of data offloading will be refers to the transferring data from IoT device to more capable systems such as edge servers, fog nodes, or the cloud. This strategy elevates resources content and enhance system performances. So the benefits will be processing efficiency, extended device lifespan, scalability, and real-time analytics. Method of data offloadings are edge computing, fog computing, cloud offloading, peer-to-peer, or P2P. So the strategy to mitigate resource constraints are efficient data handling from data compromise or selective data collections or data summarization. Uh, Energy optimization can be implement power saving modes and low power communication protocols like Zigbee or LoRaWAN. So use renewable energy sources like solar panel for the energy harvesting. Then AI at the edge. Deploy lightweight AI models optimized for IoT devices like TinyML, then TensorFlow, likewise things. Perform basic interference local while offloading complex tasks to cloud. How we can do the network optimization? Network optimization can be adapt dynamic bandwidth allocation and congestion management techniques. Use adaptive data transmission protocols such as MQTT and COAP. So these will be help to network optimizations. So, emerging trends and innovations will be federated learning, serverless computing for IoT, data decentralized architectures. So, IoT device limitations in processing and storage can be effective addressed throughout innovative strategies like data offloading, edge computing, and efficient resources management. These solutions are critical for ensuring IoT systems meet demands of modern applications while optimizing performances and energy use. So next we will talk about the challenges of cloud computing for IoT. Latency issues, network bandwidth, security concerns are the most challenges among the cloud computing for IoT. Latency issues. What is the latency issues? Latency refers to the delay between data generation, transmission, processing, and response. In IoT, where real-time processing is often critical, latency is significant concern. So, causes for this latency in network cloud computing is physical distance. The data must travel from IoT device to centralized cloud data centers, often located far from the resources, and the network delay and process queues. High demand of cloud servers can result in delay in data processing. Impact of latency. So the real-time applications will be impact of this by systems like autonomous vehicles, industrial automations, and remote surgeries requires near instantaneous response. Latency can lead to accidents uh, or failures. So the user experience also impact due to this. Delay responses smart home or IoT enabled consume device can frustrate users and reduce system efficiency. So the solutions for the latency issues mostly edge computing by process data closer to the source, minimize the need for cloud roundup trips. Content delivery network CDNS use distributed network for coaching cache in frequently asset data. 5G integrations leverage high speed, low latency network for reduced delays. Then the network bandwidth challenges. IoT devices generate massive volume of data, straining infrastructure when transmitting this data to the cloud. So causes for this bandwidth issue, high data volume, and limited infrastructure as well, concurrent device. The ex, expand, expand the expansion growth of IoT device increase competition in network resources. The impact will be caused due to these bandwidth limitations are maybe data loss, increased of cost, and this service degradations. So these will be impact will be happening as this due to the bandwidth limitations. So for the solutions, we can say data filtering and aggregations, like process and summarize data local to reduce the volume transmitted. Adaptive protocols use lightweight communication protocols like MQTT and COP, or fog computing. Fog computing also solution for the bandwidth challenge by introducing intermediate process node to share the bandwidth loads. Next, we will talk about the security concerns of uh, challenge, security concerns in challenges of cloud computing for IoT. So the IoT system rely on cloud computing for data storage and analytics, exposing them to significant security risks like data breaches, data in transit, and device vulnerabilities and compliance risk. So the type of security threat will be DDoS attacks, man in the middle attack, unauthorized access will be type of security threats. So the solutions for this, we can say end-to-end encryption, zero trust architecture, regular updates, and decentralized security models. So the future will be as IoT systems become more advanced, addressing cloud computing challenges is critical. So the emerging technologies like 6G network, quantum computing, and serverless edge platform promises to mitigate these limitations. However, the effective implementation will be requires continued innovations in architecture designs, resource management, and security practice. By proactively addressing these challenges, organizations can unlock the full potential of IoT cloud ecosystems while ensuring reliability and scalability and the security. Any doubts with this? I think no. So we'll continue for the next. So the next one is the rise of edge or cloud computing. So the edge cloud computing is an innovative hybrid parad paradigms that combines the strength of edge and cloud computing to meet the growing demands of modern application, especially in IoT. It leverages the proximity and real-time processing capability of edge computing with the scalable and computational power of the cloud. What is edge cloud computing? Edge cloud computing is integrates edge devices and systems with cloud infrastructure to distribute sorry cloud infrastructure to distribute computer session task efficiently. This collaboration optimize performances by processing critical data locally at the edge, offloading less time sensitive or resources intensive tasks to the cloud. So the key driven behind the edge cloud computing explosion of the IoT device real-time applications 5G and beyond like 6G and big data and AI. So the key features of edge cloud computing is low latency, bandwidth optimization, scalability, and resilience and reliability, as well as security and privacy. So the applications of edge cloud computing like autonomous vehicles, edge computing support real-time decisions making for navigate while cloud manages updates, large-scale simulations, and deep learning model trainers like Tesla. And the now in Italy or somewhere I cannot remember the country, they have the taxis which haven't drivers. It will be drive if we order the taxi, and when we get in the taxi it will go to the destination which we selected without a driver. So it will be happening using this edge cloud computing like autonomous vehicles. Then the smart cities and healthcare industry of IoT retails. So the challenges will be in here, interoperability and latency and bandwidth balance, resource constraints at edge, security risk, and cost management. Future trends will be serverless edge computing, AI-powered decision making, 6G networks, zero trust security models, decentralized cloud systems. So the edge cloud computing is a transformative approach that bridge the gap between the decentralized nature of edge computing and the centralized power of cloud system. It addresses the limitations of standalone edge or cloud deployments by creating a resilient, efficient, and scalable framework for modern IoT and data-driven application. As the demand for real-time analytic and intelligent systems grows, edge cloud computing will play a, play a big role in shaping and future of technology. So the clarifying the edge computing architecture, ECAS IoT, we are saying. So the clarification based on deployment location, device level edge computing by processing occurs direct on IoT device like sensors or wearables. Device handle lightweight computations and send aggregated data upstreams. Example, smart thermometers, fitness trackers. And then the gateway level edge computing, such as data is proceed at intermediate devices such as gateways or routers, suitable for filtering, uh, aggregations, and local decision making. Examples will be industrial IoT hub, home automation gateways, local server edge computing. Localized edge servers or micro data centers handle computational tasks, offers higher processing power than gateway while maintaining proximity to device. Examples will be edge servers in retail stores for customer analytics. So the network level edge computing will be data processing occurs at the edge of telecom or ISP network. ISP means Internet Service Provider. Combines proximately to device with network level resources availability. Example will be content delivery network CDNS or edge nodes in 5G networks. So the clarification based on computational distributions like centralized edge architecture, distributed edge architecture, hybrid edge architectures. So the clarification based on data flow will be reactive edge architecture, proactive edge architecture, batch processing architecture, stream processing architectures. For the reactive edge architectures, example will be security cameras acting upon motion detections. Proactive edge architectures will be predictive maintenance system in factories. Batch processing architectures example will be energy usage analysis in smart grids. Stream processing architectures examples will be traffic monitoring systems in smart cities. So the clarifications based on integrated with the cloud. So the cloud enhance edge computing like video analytic for surveillance systems, cloud dependent edge computing like IoT devices in e-commerce for inventory management. Then standalone edge computing like remote IoT installation in areas with limited internet access. Clarifications based on the functionality will be data aggregative architecture is like smart meters in utilities, real-time processing architectures like autonomous vehicles, AI-driven architectures like Edge AI in healthcare for diagnostics, and the security-centric architectures like edge computing in financial IoT systems. The resource scalability based on resource scalability clarification, we can tell fixed edge architecture like HVAC systems in smart building and the elastic edge architectures like retail IoT during peak shopping seasons. So the emerging edge computing architectures for IoT like serverless edge compute architectures, blockchain integrated edge architectures, digital twin architectures. So the conclusion will be classify edge computing architectures for IoT helps in designing systems tolerated to specific applications, balancing latency, scalability, and security. As IoT continues to the growth, these clarifications will be in all driven by advance in technologies like AI, 5G, and decentralized computing models. So, um, next one will be factors for IoT ECAS IoT. So the deployment locations like the physical locations of edge computing resources significantly impact latency, bandwidth, and resource availability. So device level, gateway level, or local server levels and network levels. So the computational distributions like tasks are distributed across devices, not all cloud different affected scalability and efficiency like centralized, distributed, and hybrid way. So data flow characteristics will be reactive, proactive, batch processing, stream processing. So the applications like healthcare, the specific industry or use case driven architecture requirements. Healthcare requires low latency, high privacy architectures. Manufacturing demands real time analytic and predictive maintenance capabilities. Transportations focus on reliability and low latency for autonomous systems. Mostly, the example which I have tell earlier, the automated taxi vehicles. Retail optimize customers' experience and innovate management. When we classifying E ECAS IoT involves considering the deployment's location, data flow, cloud integrations, functionality, scalability, and various operational factors. These factors help ensure that the architecture is optimized for its intended purpose, delivering high performance, security, and cost efficiency in IoT applications. So this is the mapping of ECAS IoT to IoT layer models, pre-paction layer, network layer, and the application layer. Pre-paction layer involves sensors and auto accurate collective and transmitting data. ECAS IoT enhance this layer by providing localized data processing for storage. So these devices and sensors that collect data from the physical environment mostly. In the network layer, what will be happening? Communication infrastructure for transmitting data to process node. So the application layer will be provide user facing services and interfaces based on processed data. So the use case of this perception layer is smart thermostats performing local temperature regulation, motion detectors that prepare video feeds before sending data. In the network layer use case, home automation systems where a local hub manage multiple smart devices. 5G enable edge nodes reduce latency in smart city networks. In the application layer, retail IoT systems providing real-time customers recommendations. Remote healthcare device offer a diagnostic based on local processing. For the advantages will be fog layer integrations, the position, role of roles, likewise. Then the cross-layer functionality. Key consideration for mapping is latency sensitive, data volume, security and privacy, scalability, scalability. So the mapping ECAS IoT to IoT layers model helps design optimize system tailored to specific requirements by aligning edge computing architectures with the functional roles of IoT layers. So AI at the edge and 6G networks will future refine this mapping and enable seamless integration for process. So the limitations will be scalability, security, standardization, and the management. So next one will be a mobile edge computing with proximity and to end user and reduce network latency. So the mobile edge computing or MEC is a transformative technology in IoT and telecommunication domains. It brings competitive storage and networking resources closer to end users, typically at the edge of mobile networks. This proximately reduces the latency optimization bandwidth and enables real-time services, crucial for modern applications. Key characteristics will be proximity to end users, MEC nodes. It means mobile edge computing. I will say MEC. MEC nodes are deployed at the edge of the mobile network. They provide localized computations, minimize the physical distance between data sources and processing point. Low latency, real-time data processing will be happens at or near the source or reduce round trip time compared to traditional cloud computing. Bandwidth optimization, context awareness, then integrated with 5G. So the advantages of MEC will be latency reduction by processing data at the network edge, Make eliminate the delays caused by data transmission to the distant cloud servers. Then the improved quality of service by localized computations and content content caching enhance user experience by reduced service interruptions and buffering. Data privacy and security. Sensitive data can be processed and stored locally, reduce the risk of breaches during the transmission to centralized cloud. Scalability make facilitate scalable IoT deployment by offloading processing to uh, distribute edge node rather than central servers. So the applications of Mac will be autonomous vehicles like vehicle to everything V2X communication powered by Mac reduce decision making delays. AR or VR and immersive gaming. So the smart cities, healthcare, like localized health monitoring with wearable devices, industry of IoT, like predictive maintenance using Mac-based analytic, reduce downtime. So the in the retail, supporting ISTO analytic for better customer engagement. Then the challenges of Mac will be deployment cost because establishing and maintaining Mac infrastructure at scale requires significant investment. Then interoperability, security concerns like the distributed natures of Mac nodes increase the attack surface, nesting to robust security mechanisms, resource constraint and standardizations. Future of Mac will be 5G and beyond, like 6G. With 5G widespread adoption, Mac will be play a pivotal role in supporting next generation applications like smart factories, connected healthcare, and integrated transportation systems. Then AI machine learnings integrated with cloud, IoT expansions, mobile edge computing or Mac is consistent of modern IoT and 5G ecosystems, enabling low latency, high performances applications that were previously impractical with traditional cloud models. By processing data closer to the end users and leveraging local contexts, Map not only reduce latency but also enhance the scalability, security, efficiency, making it key enable for the connected future. Then we will talk about the future of edge computing. The increase of adoption, advanced analytic, enhanced security. So the growth in IoT ecosystem, explosion in IoT division by 2030, the project that there will be over 50 billions connected devices worldwide. Uh, so the edge computing will be the backbone for 5G and beyond by ultra low latency network slicing, integration with 6G. So the emergence of Edge AI, like decentralized AI models, federated leasings, real-time decision making, hybrid architectures like seamless integrations, hierarchical models, dynamic offloadings. Those will be the future of the IoT. So the so challenges ahead will be while the future of edge computing and IoT is promising, there are challenges that need to be addressed like scalability, managing billions of devices, and edge nodes will be required innovative architecture and resource management solutions. Then the security risk, they are going to distribute the nature of edge computing, decrease the attack surface, and secure the requiring robust security mechanisms. So the future of edge computing and IoT is poised to revolutionize industry by enabling faster, more efficient, and more secure data processing. As these technologies mature, mature, they will unlock new possibilities in areas like AI, 5G, sustainability, and the smart environment. By addressing current challenges and embracing advancement, edge computing and IoT will become the cornerstone of the connected world. So next we will talk about the hybrid and multi-cloud architecture. So the uh, definition of hybrid and cloud architecture is important in modern IT infrastructure. Key trend during the adoption will be uh, key trend driving adoptions. So the what is cloud? Hybrid cloud. Components of hybrid cloud architecture and common use case. Just a moment. Yeah. So the these key concepts, benefits, and consideration involved in the creating and managing these complex and var varieties in IT environments. So next, we will talk about on-prem and cloud integrates. So the on leveraging existing assets, uh, hybrid architecture bridge a gap between on-prem infrastructure and in info cloud services. Like I will tell like this. So the balancing legacy systems with modern capabilities. Benefits will be flexibility, cost efficiency, and leverage existing investments. So the challenges will be complexity and compatibility and security considerations will be there. So the key consideration for integrations like assessing current assets, inventory of on-prem systems, identify legacy systems that can be migrated for extended evaluation, current network and storage capacity. Define integrated objectives like performances improvements, cost reductions, and enabling scalability or disaster recovery. Then the hybrid cloud models will be workloads split between on-prem and cloud environment. Specific use cases will be data processing, backup, or bursting. So the tailored solutions for on-premises and cloud integrations are application modernizations, rehosting, moving existing applications as is. So refactoring, adjusting applications for cloud compatibility, rebuilding, create cloud native solutions for existing workflows. Data integrations. Data integrations is synchronization database between on-premises and cloud environments. Tools like AWS database migration services, Azure Data Factories, Google Data Flow. Then network and connectivity, such as secure connectivity using VPN or direct connect services, implementing SD-WAN for efficient traffic management. Identify and access management, extending on-premises Active Directory to the cloud using single sign-in for seamless user access. Automation and Orchestrations leveraging CI/CD pipelines for integrated developments and deployments, tools, uh, Terraform, Ansible, and Kubernetes. Leverage leveraging existing assets, excluding legacy systems, APIs to expose legacy functions to cloud-based applications, middleware for integrated without distributions. Hybrid storage solutions like integrating on-premises storage with cloud services like AWS storage gateways or Azure file synchronizations. So the cost optimization is reusing existing hardware for private cloud components, strategic placement of workloads to minimize cloud expenses. Vendor collaborations working with cloud provider to optimize for specific hardware platforms. So the retail industry integrated post system on premises with cloud-based analytic for real-time inventory tracking. In the healthcare, extended legacy EMR systems to cloud for telehealth solutions while maintaining compliance. In manufacturing, connected on-premises IoT data system to cloud AI tools for predictive maintenance. Challenges and solutions in here: compatibility issues. Challenge will be compatibility issue, and the solution can be use abstractions layer or middleware for this. For the security concern challenge, we can use hybrid identity management and encryption. For the latency and performances, solutions can be used as deploy edge computing or low latency connections. So the for the holistic strategy, successfully integration required balance on-premises reliability with cloud scalability. For the leveraging existing investment, maximize ROI while reduce transition risk. For the future outlooks, we can use advance in edge computing and AI will further enhance integrate capabilities. So the next one will be workload uh, portability. Enhance flexibility, reduce vendor lock-in, and streamline migration in migrations. So the ability to move applications, services, and data seamlessly between on-premises to premises, private cloud, and multiple public cloud environments. Why this matter? To avoid over reliance on a single vendor, enhance flexibility for scaling and adaptive of challenging business needs, simplifying migration and disaster recovery plan. Key goals will be interoperability across platforms, minimize downtime and disruption during the migrations. Benefits of workload probability will enhance flexibility, reduce vendor lock-in, streamline migrations, optimize cost and performances. Key considerations for achieving workload probability will be containerizations. Use tools like Docker or Kubernetes to encapsulate applications and their dependencies, enabling deployment on any platform supporting containers. Cloud cloud agnostic design, like develop applications using standard APIs and open sources tool to ensure compatibility across platforms. Data portability, implement storage solutions that support standard protocols like NFS S3 compatibility APIs. Use data replication tool to synchronize across environments. Define uh, architectured and management. Leverage architectured platforms like Kubernetes or HashiCorp Node. to manage workload across cloud. Then the security and compliance ensure data and applications meet regulatory requirements regardless of the environment. Employ employ consistent security policies and encryption strategies to reduce the vendor lock-ins like avoid proprietary tools, abstract platform dependencies across cross cloud networking, regular testings. So the streamline migrations, asset and planning, incremental migrations tools can be used as like AWS migrations, Hub, Azure migrations, or Google migrations for compute engines. So the validation and optimization test workload in their new environments for functionality, performances, and security. Use cases will be disaster recovery, replicate workload across cloud to enable rapid failover and reliance, busting for peak demands, optimization, geographical distributions, uh, like deploy workloads closer to the end user by leveraging multiple cloud regions. Then the challenges and mitigations. Uh, Interoperability issues. This can be mitigated by use standard format and APIs. Data transfer overhead. This can be mitigated by optimized data movement using WAN, accelerated or edge caching. For the security and compliance risk, maintaining unified security policies and consistent encryption practice. So the workload probability empowers organization with flexibility, cost efficiency, and reliance. By leveraging open standards, modern tools, and careful planning, business can be achieved reduce vendor locks in and seamless migrations. So next we will talk about the data disaster recovery solution. What is a disaster recovery or DR? A strategy to restore IT systems, applications, and data after disruption, ensuring minimal downtime and data loss. Why it's crucial? Just a moment. So the protects against natural disasters, cyber attacks, or hardware failures, maintaining operational continuity and customer trust, align with compliance requirements for data protections and availability. So the key objectives of DR will be business continuity, enhance resilience, disaster data security. So the type of disaster recovery solutions will be backup and restore, uh, pilot light strategy, worm Stanley, hot standby, disaster recovery as a service, we are telling at DRAS. So the outsourced disaster recovery hosted by the third party, best for organizations without in-house expertise or infrastructure. Providers will be Certo, Datto, Carbonite, and the Azure DRAS. So the key components of disaster recovery solutions is data replications, failover or failback mechanisms, cloud integrated testing and validations, or security measures. Step for the designing this effective DR plan, like risk assessment and impact analysis, identify potential threats and their impacts on the operations, then set objectives like define RTO, define RPO. It mean RTO mean recover time objective, RPO mean recover point objective. Then they choose the right solution. Then implement redundancy, automate DR process, and continuous monitoring and optimizations. So the challenges will be cost management will be a challenge for this. We are use cloud-based pay-as-you-go DR services. For the different regular across regions, impact geofencing and region-specific compliance solutions. So, by the leveraging cloud integration, automation, and business can be minimized downtime and maintain trust during distributions. The future of DR lies in AI, edge computing, and blockchains. So next we will talk about multi-cloud deployments. What is multi-cloud? A strategy where an organization use services from multiple cloud providers like AWS, Azure, Google Cloud to optimize performances, flexibility, and resilience. Why multi-cloud is need? Avoid vendor lock-in, leverage the best capabilities of each provider, enhance fault tolerance and disaster recovery. So the challenges of this multi-cloud is complexity and the integration issues and the cost management. So the uh, key benefits of this will be vendor flexibility, cost optimizations, performances improvements, enhanced reliance, resilience, compliance and data security. So the components of this multi-cloud deployment is compute, storage, networking, security and identity management, and monitoring. So the strategic for cloud multi-cloud deployments will be workload segments, data replication and distributions, multi-cloud application design, and hybrid integrations, as well as disaster recovery or redundancy. So the key tools and the technologies of this multi-cloud deployments will be CMPs, cloud management platforms, or, or orchestration tools like Kubernetes, Terraform, and Ansible. Monitoring and observation should be done. So the cost like Prometheus, Grafana, and Splunk for the performance tracking. The cost management can be done from Cloud Health, Spot.io, or FinOps. So security tools like multi-cloud firewalls, like Palo Alto Prisma Cloud, Checkpoint Cloud Guards will be help. So centralized identity management with IAM tools like Okta or Ping Identity. So the complexity of management challenge solution can be use centralized CMPs and automations tools. For the data transfer overheated, we can optimize data transfer path using CDNs uh, or edge computing. So, multi-cloud deployments offer unparalleled flexibility, reliance, and performances benefit for modern enterprises. While challenges exist, strategic planning, robust tools and best practice ensure successful implementations. As technology evolves, multi-cloud will remain a cornerstone for future-proof IT strategies. So the cross-cloud redundancy. What is cross-cloud redundancy? Cross-cloud redundancy involves deploying workloads, data, and services across multiple cloud providers to ensure high availability, fault tolerance, and disaster recovery. Uh, why this is critical? Mitigate risk of a single cloud provider failure, enhance reliability and resilience, safeguard data against regional outstand or cyber attacks. Core components of cross-cloud redundancy will be data replications, increased reliability, data security, like encrypt data in transit and rest. So the benefits of the cross cloud redundancy will be fault tolerance and high availability, optimized performances, compliance and data sovereignty, like store data in compliance with regional regulations by leveraging multiple geographical locations, cost efficiency, scalability, and flexibility. So the strategies can be take for the implementing cross-cloud redundancy is active deployments, active passive deployments, geo-redundant storage, load balancing across cloud, and unified backup solutions. Tools and technologies will be data replications tools like NetApp, Dell EMC, cloud native tools like AWS S3 cross regions for the Ocean's platforms, Cognet and HashiCorp. Monitoring and observability tools like Prometheus and Grafana, Datadog for unified insight into cloud platforms. For the identify and security management, Okta, Azure AD, Ping Identify for cross cloud IAM, uh, Palo Alto, Prisma Cloud, and AWS Security Hub for the policy enhancements. For network optimizations, we can use SDN solutions like VMware, Cisco, SD-WAN. In the best practice part, we can say adaptive cloud agnostic architecture, automative failover mechanisms, implement data encryptions everywhere, likewise things. So the challenges will be integrations complexity. So the solution, we can use abstraction layer and cloud management platforms. For the latency and data transfer overhead, we can use optimized data routes using CDNs and edge computing. For the security gaps, implement unified security frameworks and real-time monitoring. For the cost management, regularly audit usage and align cost with business priorities. So the cross-cloud redundancy is essential for modern enterprises seeking high availability, reliability, and robust data security. By adopting the right tools, practices, and strategies, organizations can mitigate risk and optimize performances as well as future-proof their infrastructure. So the next vendor diversifications. So what vendor diversification or diversifications? The strategic approach where organization leverage sorry. The strategic approach where organizations leverage multiple vendors for product or services rather than relying on a single provider. This ensure flexibility, reduce risk, and foster innovations by exposing business to diverse technologies and solutions. Core benefits of vendor core benefits will be reduce risk, enhance negotiations, increase innovations, and uh, increase innovations like access to diverse solutions and emerging technologies. Key strategies for vendor diversions are asset corruption dependence, adopt a multi-vendor approach, establish vendor benchmark, leverage open standard and interoperability, foster vendor relations, implementing vendor diversions like procurement policies, pilot programs, diversity cloud provisions, invest in vendor management tool, prioritize security and compliance. So the benefits will be resilience against this disruptions, enhance bargaining power, encourage innovations, global reach, and localized experience. So the uh, vendor diversifications is a strategic necessity to today's dynamic business environments. Uh, environment. It reduces risk, foster innovations, and enhance bargaining power while ensuring optional resilience. So, next, the last main topic will be emerging trends in enterprise technologies. So the what are the emerging trends in enterprise technologies like AI, machine learning, cloud computing, cybersecurity innovations, intents of things, Internet of Things, industrial IoT, then quantum computing, 5G and beyond, sustainability of and green IT, blockchain, Web3 technologies, then remote work and collaboration tools, data privacy and governance, low code of non-code platforms, and generative AIs. So like ChatGPT, Copilot, likewise things. So we will talk about the serverless computing 2.0, overcoming limitations and advancing capabilities. Serverless computing has revolutionized application development by abstracting infrastructure management, enabling development uh, to focus on write code. However, as adaptive grows, so do its limitations and expectations. The next phase, serverless computing 2.0, address these challenges and expand in its capabilities. Challenges in current serverless computings like cold start, vendor lock-in, limited long-running tasks, debugging and monitoring capabilities, resource management constraint. So advancing capabilities in serverless computing 2.0 is stateful serverless, combining serverless with state management for more complex overload. Example, durable functions in Azure, step function in the AWS. So the next one is edge serverless, processing functions closer to the user for ultra low latency. Example, AWS Lambda at edge. Cloudflare workflow, event-driven, event-driven tasks. More robust support for event-driven workflows across distributed systems, AI and machine learning integrations. Improved developer experience, security enhancements like serverless, specific security measures like function shield, granular IAM policies, and runtime protections. Eco-friendly compute optimized for energy efficiency, contributing to sustainable goals. So the future possibilities with serverless 2.0 will be composable services, hybrid cloud serverless, self-healing functions will be there in the future. So the serverless computing 2.0 address the limitations of its uh, pre predictions while unlocking new possibilities by overcoming challenges like cloud starts, vendor clocks in and limited observability. So the next one will be stateful serverless, enabling persist data and stateful workloads. So stateful serverless is an advancement in serverless computing that allows developers to manage stateful workloads, tasks requiring memory of prior operations while maintaining the scalability and simplicity of serverless architectures. This addresses key limitations of traditional serverless models, which are inherently stateless. So the challenges will be uh, ephemeral nature, workarounds for state management. The key components of stateful serverless will be durable state management, event sources, and state machines in memory state for low latency. So the advantages, stateful execution models, technologies like Azure Durable Functions and AWS Step Functions introduce mechanism to store and manage state internally. So distributed state management platform like Apache, Kafka, Streams and Apache Flink integrate state with distributed system for real-time analytic integrations with uh, persistence storage like tight coupling with stateful databases like Dynamos DB, Cosmos DB for seamless state retail storage. So the benefits will be simplified architectures by reduce the needs for external state management and decrease in operational complexity. Enhance application use cases like workflow, session management, real-time analytics. Also improved developer productivity by focus shift to building business logic rather than managing state infrastructure. So the platforms will be used in here: Azure Durable Functions, AW Step Functions, Cloudflare Durable, and Temporal.io. Future directions will be AI assistant stateful workloads, hybrid stateful models, decentralized states. So next we will talk about event streaming architectures. So event streaming architectures enable organization to capture, process and analyze a stream of real-time data from various sources, delivering actionable insight and driving responsive applications. These architectures have become a cornerstone for building modern reproductive systems. Core concepts will be events, event streams, producers and consumers, stream processings. So the key components will be event broker, stream processing frameworks, data storage, event consumers. Benefits will be real-time insight, scalability, decoupled system flexibility. So popular tools which and frameworks which is used in event streams will be event brokers like Apache Kafka, Amazon Kinesia, Google Pub or Sub. For the stream processing, Apache Flink, Kafka Streams, Apache Park Streaming. For the data virtualization and analysis, ELK, Elastic Stack, Grafana will be used. For the event stream architecture empower business to leverage real-time data pipelines for agility, representative, and innovations. So next one will be quantum computing breakthroughs. So the quantum computing leveraging the principles of quantum mechanisms has seen remarkable progress in recent years with the advancement in hardware algorithms and particular use cases. It is edging closer to achieving quantum supremacy, the point where quantum computers outperform classical systems in solving specific problems. Among its most transformative potential applications in cryptography, which could redefine security paradigms. So the key concepts will be qubits, quantum entanglements, quantum supremacy, quantum decoherence. So the breakthrough driving quantum supremacy will be Google Sycamore processor in 2019, IBM quantum volume matrix, fault tolerance quantum computing, photonic quantum computing, quantum algorithm innovations. The applications in cryptography will be threat to current cryptography, like applications in cryptography, like threats to current cryptography, like show algorithms, RSI, ECC encryptions, Grover's algorithms. So the quantum resistant cryptography, like NIST is standing quantum safe cryptographic algorithms. So now we will talk about challenges in quantum computing and the how we can overcome it. Is scalability. Building systems with millions of errors corrected qubits remains a significant hurdles. So decoherence and noise. Developing robust error corrections methods. Interoperability, creating frameworks to integrate quantum systems with classic computer workflows. So the quantum computing is redefining the limits of computations and security. Its breakthrough towards quantum supremacy and applications in cryptography signal a transformative shift across industries. So next, we will talk about neuromorphic computing. This is like a brain impressed architecture for efficient AI ML process, artificial intelligence or machine learning processes. So, neuromorphic computing mechanisms, the structure and function of biological brains to create hardware and system capable of effective low power computations. This emerging paradigms is particular promising for advancing artificial intelligence AI and machine learning ML enable real-time processing, energy efficiency, and adaptability. Key principles will be spiking neural networks, SNNs. Unlike traditional neural networks, SNNs process informative via discrete spike mimicking biological neurons communications, support event-driven computing using redundant operations. Plasticity, dynamic adaptation of synaptic weight increased by Hebbian learning allows system to learn and evolve in real time. So the components of neuromorphic hardware is artificial neurons and synapses, crossbar arrays, memory storage, event-driven sensors will be components of neuromorphic hardwares. So the advantage of neuromorphic computing is energy efficiency, real-time processing, scalability, and robustness. So the applications which is used in here is Edge AI, enable AI processing directly on device, reducing dependencies on cloud computing. Example, real-time image recognition on smartphone or IoT devices. Robotics and autonomous systems facilitating low latency decision making and learning, enhancing native navigation and interactions. In healthcare, efficient processing of biomedical signals like EEG or ECG for diagnostic and wearable health monitoring. So the prominent of uh, neuromorphic platforms like IBM TrueNorth, Intel Lohi, SPY NNK, University of Manchester, brain scales will be prominence of neurometric platforms. So the neurometric computing in AI or machine learning is training efficiency, implement online learning directly on hardware, reducing training overheads. So the sparse data handling, enhanced explainabilities will be the biological inspirations make neuromorphic models more interpretable compared to deep learning black box models. So the future directions will be integration with AI and machine learnings, hybrid architectures combining neuromorphic and traditional computing for enhanced versatility. Like in the movies, it's showing like iRobot or most of sci-fi movies are based on these things. The integration of AI or ML, machine learnings, with our brain, our neurons. So it will be the next future of the neuromorphic computing. So brain machine interfaces, autonomous systems, quantum neuromorphic surgeries. So the neuromorphic computing offers a transformative path for a artificial intelligence or machine learning, emphasizing energy efficiency, real-time processing, and adaptability. As the technology matures, it holds the potential to revolutionize various domains. So, this is the end of third lecture and the end of our server architecture. Next week, I will be going to do the lecture on operating systems. It will contains the operating systems which is used in our day-to-day lives. Okay, for now, the sessions will be ended and we will see you on next Saturday. Thank you.
Thank you, sir.